So today I'm going to, in this first lecture, I'm going to give an application of network flows. Yesterday you already saw quite a few applications in Meghna's lecture. For example, for finding a maximum matching in a graph, in a bipartite graph, you can apply MaxFlow and solve it. Finding a maximum collection of edge disjoint paths, and then you probably also saw some examples in your problem sheet. So today I'm going to give a non-intuitive application. I mean, when you think of network flows, you think of a graph, something flowing, some liquid, something kind of an image. But the problem I'm going to do is completely non-intuitive, that why you would use network flows to solve this problem. So we'll see. Okay. So the problem is back to the IPL game. Let's say we have 4 teams in running. I mean, not anymore in this season. I know it's all over almost, but let's say somewhere in the middle, we have, these are the 4 teams surviving with the following scores. Okay, so CSK has 12 points, Rajasthan has 11 points, Kolkata has 11 points, and Sunrisers has 10 points. And there are still a lot more games left. Okay, so this is a league match. In IPL, everybody plays against everybody else twice, but in many leagues, in baseball and football, they play the whole tournament happens throughout the year, and everybody plays a huge number of games against each other. So let's assume the number of matches left at this point are, there is one more match So these are the 5 matches left. Okay, and I'll assume there are no ties, and the current scores are here 12, 11, 11, 10. These are the 5 matches left. And the question is, can Sunrisers Hyderabad survive? What do I mean by survive? Can get score at least as high as the top. Okay, so you still have so many matches left. Is there some possibility of outcomes of these matches such that Sunrisers Hyderabad has still a chance of at least getting as much, at least tie with the last game, the top team? Let's see, will it survive? Okay, so Sunrisers, let's say, is your favorite team and you want it to survive. So let's think of some cases, right? What do you want the outcome of this match to be? Sunrisers wins, right? You want this match, you want to see the possibility of Sunrisers making it to the top. This also you want Sunrisers to win. But that's all the matches for Sunrisers. So the maximum score it can get is 12, right? So Sunrisers can, at best, can get 12. Okay, good. You don't want CSK to win anymore, because then this guy will go up beyond this, right? So that also gives you that RR wins, KKR wins here. So, what happens to the score so far? Rajasthan has become 12, Kolkata has become 12, but there is still one more match left between Rajasthan and Kolkata. One of them has to get 30. There are no ties. So, the answer is no, right? Given even the best possible scenario for Sunrisers, somebody is going to get a score of 13 and Sunrisers have no chance of surviving. Okay. So, we did some case analysis, but imagine so this is an important practical question, right? If you are a sports journalist and you are in the middle of a team and you want to tell your viewers, is your favorite team has any chance at all, there are all these possible case analysis one has to do. But here is another simple argument to say that Sunrisers cannot survive. Let us look at these three teams, right? How many matches left among them? There are 3 matches left, right? So, totally 3 matches left and one of them is going to score them, right? Plus their current score is 12 plus 11 23 plus 11 34 plus 3 37. Totally wins possible among these 3 37. So, one of them out of the 3 is going to get more than 12, because you need to distribute 37 to 3 players. One of them is going to get more than 12, whereas Sunrisers can get the maximum 12. Okay, so here is another averaging argument that which is that CSK's current score plus matches to be played plus for the other 3 teams divided by 3 is strictly greater than 12, whereas SRH can get at most 12. Okay. So, let us think of the more general version of the problem. What is given to me is input some n teams, their current scores, right. So, there is number of matches they have won. So, these numbers are given to me. What else is given? Matches to be played, right. Matches to be played is essentially a graph or a multi-graph, if you like, right. So, you have this GXY games left between X and Y. And let us say we are focusing on some player number 1, then what we argued is the following from this example. Player 1 cannot survive if, when I say survive, you know what I mean, that does it have a chance to make it to the top, at least with the tie in the score, if summation Wi I greater than or equal to 2 plus summation Gxy x and y are not equal to 1 divided by n minus 1, if it happens to be greater than what? Just W1? W1 also has more matches to be played, right? It can win all of them, assume, plus G1x x not equal to 1. Okay. A lot of people said I like math. Okay. So, here is a formula we saw from a simple example. Now, I just this is all Greek and something, whereas in the previous example there were some numbers. So, the input is a bunch of games, each team has won, and then there are some GXY games left between teams X and Y, and let us say I am interested in player 1, and what we saw is the player 1 cannot survive if the wins of the remaining teams plus the games they have to play divided by n minus 1, that is the total number of teams if you omit 1. If it is greater than the maximum the first player can win, which is W1 plus summation G1x. Okay. Now, the interesting question is the converse true, right? Is it, suppose this does not happen, then is it true that player 1 can, is there some sequence of outcomes so that player 1 can actually survive and make it to the top, right? So, let us look at another example. Let us look at another example to show that the converse is actually not true. These are the current scores, the matches left. This team has 4 games left between each others. There is 1 game left between these 2 teams, and there are some 6 games left between these 2 teams. Suppose I have pictorially drawn the graph on the matches left. There are 4 matches left between SRH and RR. There is 6 matches left between Kolkata and Chennai, and there is 1 match between left here, and SRH is 4 matches between all other teams. Okay. Let us do the averaging argument again, right. So, what is the maximum score SRH can get? (21), right. There are 12 matches left and it already has a score of 9. So, maximum it can get is 21. Let us look at the average here. The average here is 20 plus 18 plus 17 is the current scores, plus how many matches are left among them. There is 1 plus 1 2 plus 6 8 matches left, and there are 3 teams. What is this number? 63 by 3, which is 21. So, there is a sequence of outcomes so that, well, I am not saying that yet. I am just saying that this averaging we said fails here, that it says that the average here is 21, but is there some sequence of outcomes so that SRH will, so because this, what we know is if this happens, player 1 cannot survive. I am not necessarily saying if this does not happen, player 1 can survive. We do not know that. That is the converse question, and that is what we are discussing, right. So, here is an example where that averaging does not happen, these 2 guys match, but I want to argue that still there is a problem, and the problem is to look at these 2 teams alone, ignore RR for now, look at CSK and KKR. Their current score is 37 and there are some 6 matches left. So, there are 43 divided by 2 is greater than 21, right. So, if you look at just these 2 teams, their current score is 37, there are 6 matches left, right. So, I claim that one of them is going to get more than 21, right, because it is just the same kind of an averaging argument, not on the entire 3 teams, but just on the 2 teams, right. So, because this is 37 plus 6 43. So, you do not want this guy to go beyond 21. So, CSK can maybe get exactly 1 match, that forces this guy to win 5 matches. So, it will get to 22. Okay. So, even though the averaging is not true for the whole set, what we observe is that for some subset it is true. So, now I am going to make another conjecture. So, player 1 does not survive if there exists some subset of the teams, not the entire set, but some subset such that the number of wins they have plus the number of games they are yet to play divided by the number of teams, if that is greater than the maximum SRH can get. What is the maximum? W1 plus summation G1x, where x is not equal to 1. This is the maximum this first player can get, and if this average, so the first conjecture was that for the entire remaining set of teams, but now we saw an example where this is not true. But what is true is that even if there is some subset of vertices for which this happens, then also the player 1 cannot survive. Okay. But if I want to answer this question, okay, so now I am going to now say that it is not only if, but it is if and only if. We will prove this, that if there is no such subset, then there is some combination of outcome of the game such that my chosen player can win, okay, or chosen team can win. Now, how fast can we check this? Suppose this is even true, I need to prove this. How fast can we check this? There are too many subsets to check, right. Once you fix a subset, this number is easy to calculate. I know what my player 1 can get, m is easy to calculate because it is from the input W1 plus summation G1x. If you fix some subset, I can compute this and verify whether it is greater than m or not. But can I mean, how many subsets of what 2 to n are there? How many subsets are there? 2 raised to n minus 1, right, because this is an n minus 1 size. So, that is an exponential number. You can ask, so what? That will be the topic for the next week, right, exponential algorithms and polynomial algorithms. But this is an inefficient algorithm if you just want to run through all possible subsets and check this. But what we are going to see is that there is a way to model it as a network flow and run one iteration of your network flow algorithm, and it will tell you whether such a subset exists or not, using not just running max flow min cut algorithm, max flow algorithm, but also using the max flow min cut theorem. Okay, so we'll need both of them. Okay, so what is now now we want to reduce it to a network flow problem, and so a network flow requires a graph, a directed graph, and an S and a T. So how do we model it? So what is it we are trying to find? We are trying to find the outcome of the remaining games, right? So that is the unknown thing, right? If I wait long enough, I will know the outcomes. So what is it I am trying to find out is the outcome of the remaining games. How do they, is there a way in which they will proceed so that my chosen player will not lose, or it will match it to at least to the top scorer. Okay, so I am going to have a source S and the T we needed for my network flow problem, and this source is going to supply the outcome of the remaining games, right? That is what we need to determine. So, what are the vertices for? So, here I will have xy pairs of the vertices such that gxy, the number of games left, is strictly more than 0. I am going to have such pairs of vertices here. These are the vertices corresponding to the games, right? So many games are left. And these are the vertices minus 1, because the first vertex is what I am interested in. And let us calculate this quantity m, which is W1 plus summation G1 x not equal to 1, right. This is the maximum my chosen player or team can get. Okay. So, now I am going to have my directed graph like this. right? These are the vertices in the graph, sorry, there is no graph, the teams, right? Our input is a set of teams, right? So, those vertices correspond to the teams except my interested player, and these vertices correspond to pairs of teams between which some games are left. Okay. So, now, so if this is a game between x and y, there will be a directed edge to x and there will be a directed edge to y. And the interpretation is that in this game x wins means I will go use this edge, y means 1 means that I will use that edge. Okay. So, now my directed graph is clear, right. This is my entire directed graph. There is S, T, games, vertices and adjacencies are defined. Now, I have to throw in, what do I need to throw in for network flows? Capacities. So, I am going to throw in capacities now, right. So, what are the capacities I am going to say? Well, for an xy team pair, I am going to give a capacity of gxy, right. These are the number of games left. Out of these gxy games, some number, so if I want to preserve conservation in network flows, if there is a flow of gxy that goes here, some of them will go to x, some of them will go to y, okay, corresponding to some player, some match x wins, some match y wins, okay, good. Now, so in the flow, how many, what would be the flow coming into x, let us say. Okay, suppose I ran max flow with this, I haven't still told the capacities yet. The amount of flow that will come into x is what? Number of matches? 1 by x, exactly, right. So, number of matches 1 by x is what is going to come, because my interpretation I told you this corresponds to matches and anything that comes here is 1 by y. So, number of matches 1 by x will come here and I am going to put a capacity here of m minus wx. Okay. What does that mean? That I do not want you, right, to satisfy my goal, I do not want x to win more than m minus wx games. M is the maximum my player is allowed to win and you already won wx, I know it from my input. So, I am going to put a capacity of m minus wx, right. So, if more things come, they can't get out here, there will be conservation. So, there will be some problem, we will come to that what problem is. So, the capacities on these edges are defined now, the capacities on this edges are defined, and what I have not told you is the capacities on these edges, well, they can at most be gxy, right. But for some convenience in the proof, I am going to actually give a high capacity. I am not, it turns out that if I give a large infinite capacity, the proof makes it simpler, but one can also work with. So, we are not going to worry about the capacity here, okay, assume there is infinite capacity. So, now this is my directed graph with S and T and capacities, and so that is a network flow problem. Okay. So, now let me define one more term, which is G star is summation gxy. Okay, xy pair is, yeah, you know what I am talking about. So, here is my directed graph with S and T and nodes and edges and capacities. Tell me what this means. Suppose max flow in this network is G star. What does that mean? Let us stare at this network again. Yeah, so suppose max flow in this network is G star, what does that mean? So, I have a directed graph, I run my max flow. What does that mean? Suppose max flow is G star, what does that mean? Your team will survive. Okay. Yes, correct. Let us see the argument, right. So, that means every edge here is saturated, right. There is a total flow is G star, that is what is maximum possible, because that is the capacity out of S anyway. Capacity out of S is G star. You can't have a flow beyond that anyway, because these edges can take only that much. Suppose the max flow is G star, that means that all these edges are saturated, right, in my max flow. That means there is a way to split this GXY games in a way that here only M minus WX goes through for each of these edges, right. So, there is a way to predict the outcome of these GXY matches, because network flow will tell me, when I run the network flow algorithm, it will tell me out of the matches, 25 matches left between X and Y, 4 is 1 by X, 6 is 1 by 21 is 1 by Y, or something like that. Whatever the solution to network flow will tell me a way in which this GXY summation GXY matches can be distributed, because these capacities are determining that my team will survive, because whatever it is, if you can execute all the matches meeting these capacities, that means that nobody is going to get a score of M or more than M. Maximum they can get is M, right. So, then team 1 or player 1 is not eliminated. I.e., there is a set of outcomes of the G star matches left, so actually number of matches left is not G star plus the matches with 1, but let us assume that those matches my team wins. Okay. So, that is the set of outcome for those matches, for the remaining G star matches left, so that no team wins more than M matches. Why is that? Because you get it from the flow. So, you run max flow, and max flow tells you that here is the flow, it will tell you some positive number on each of these edges. If the max flow is equal to G star, all these edges are saturated, there is a flow of GXY on each of these edges. Because of conservation, that GXY should go, some of them should go to Y, some of them should go to X, right. That tells you the outcome of these games. And because this capacity is limited by M minus the number of wins by that team, totally what will go into T is never more than M for any of this, right, M minus W of that. So, if you include the already 1 points, it will never be more than M. So, if max flow is that, I will get it. So, here is a polynomial time, okay. We have not seen a polynomial time algorithm for max flow yet, right? Yes. What kind of running time have you seen so far? What is the running time of max flow, Ford-Fulkerson algorithm you have seen? More precisely, worst case it's exponential, okay. Okay, you are all turning your pages, okay. M, if M is the number of edges, right. So, you have seen examples, we will see it in the next lecture, where Ford-Fulkerson actually augments it just by 1 every time. So, the max flow, there could be max flow can be 2 power 10 or something based on the capacity, right. Well, I can show it here, that I am sure you would have seen this example, right. Suppose these are the capacities and I want to run max flow on this algorithm, okay. By some unfortunate event, the residual network picked up this graph SABT, okay. So, what is the maximum flow you can push through this path? 1 because of this, right. So, you will get 1 flow, right. Now, because this edge is saturated, this BA edge will come in the residual network, right. So, next time suppose it picks this, then it will go from, it will pick whatever is left. Is it clear? Have you seen this example, or we will run it again? Okay. It can run whatever is left one flow, but then this is restricted by a capacity of 1. So, it is possible that say every time to construct the residual network and to find a path takes how much time? Order m time, because it is just a breadth first search or some search in a graph, right. Lecture 1, right. So, just to find whether there is a path from S to T, what do? You just some DFS or BFS or something that takes order m plus n. M is the number of edges and n plus n is the number of vertices. That is exactly what you do on the residual network, right. So, you start with some 0 flow, construct the residual network, constructing will take some order m time. And then in the residual network, you will find an ST path which takes a BFS or DFS, and then push the flow whatever is restricted flow through that, and you keep continuing this, right. So, it is possible that you will run this whatever a million times, if that is the size of the flow. So, even though it is a very small graph, right, there are 1, 2, 3, 4 vertices, but the running time of the algorithm, if you are not careful enough, it can take as bad as order m times the flow size. Okay. But turns out for the applications you saw, finding maximum matching, Koenig algorithm and edge disjoint paths, the capacities are all 1 or small number. So, you can, it is not a big deal, but sometimes it can be a big deal. So, in the next lecture I will actually give you a polynomial time algorithm for finding max flow, where the polynomial does not depend on the capacity, it just depends on the number of vertices and the number of edges. Okay. We will see that next time. So, there is a polynomial time algorithm. So, running a max flow on this will tell you that you run the max flow, your polynomial time algorithm, set up this max flow network, run it, it will tell you if the flow is G star, then team 1 is eliminated. Okay. If the flow is less than G star, can I say that team 1 is eliminated, right? I want to argue that, because I said it is an if and only if. That is not obvious, right. It is obvious that if you run the flow and if the flow is G star, that means that every game can be has an outcome based on the network flow solution such that nobody wins more than m matches. So, you run max flow, and if it is G star, great, you got it. But if it is less than G star, then can I be sure that there is no combination which will give you, make your team win. And the way we are going to prove it is by showing this, that if the max flow is less than G star, I will exhibit you a subset of teams who will satisfy this. And how will I execute this? Can you guess? How does max flow will give me such a set? Because when we reach max flow, what do we know? We know min cut. So, the max flow min cut theorem, the duality will actually tell me that, oh, your max flow is less than G star. So, the min cut is less than G star. Give me the min cut. I will take the min cut. From that min cut, I am going to get you a set T for which this is satisfied. We know that if this happens, player 1 has no chance. That we have seen, because one of them is going to get something greater than m simply by this averaging argument. But I said finding such a T brute force can take exponential time, but you do not need to run max flow. If max flow is G star, I will give you a sequence of outcomes for the game so that my team will survive. If the max flow is less than G star, then I will argue in the next 10-15 minutes that I will produce you a team that satisfies this condition.